So let's move to the next topic of the day, which is basic cameras. How do basic cameras work? We already saw from last time that if we put a lens in front of a wall, we're going to get an image. And a camera is just using that trick. So we put a lens in front of a film or a CCD, and that image that was cast to the wall in the demo from the last class, or the class before that, is just recorded on the screen. So the camera in its most basic form is just a lens with some photosensitive backing. So it's a lens with something in the back. Typically it's a CCD to make a digital image. Or if you're in the olden days, or you're a hipster, you can use just film. Both of these things effectively record the amount of intensity of light that strikes it, and we're basically just making an image exactly like we did before. So each point on the object space is going to be mapped to a point in image space, and that's just going to get recorded on the film. So there's a few nuances with cameras. So first of all, the focus has to be at the right length. So typically there has to be some way to adjust the focus. So we need to be able to move this lens back and forth. More complicated cameras will have several lenses, but we know how to analyze that now. And we're going to reach a point where we need to get enough light hitting either the CCD or the film to expose a picture. But if we get too much, everything's going to be completely saturated. We're going to either get full voltage or 255 bits on the registered on the pixel in the CCD, or for the film it's going to be completely developed. So one way to do this is to adjust our so-called exposure time, or the shutter speed. So typically there's going to be a shutter, doesn't really matter where it is, that will adjust how long you let in light. But even this typically is not enough to completely take a perfect image. The reason is you might be in a very dim lit situation where something's moving very fast. So you want to take an image at an instant in time. Of course, that's impossible to take at an instant of time, but you want to take it very quickly, say in a millisecond. So you set your shutter to open for a millisecond, then close. And then whatever photons you get hitting that film, that's what you get, and you don't get upset, but you might get an underdeveloped photo. So you want to allow more light in. Similarly, you might have a very, very bright source, but you might want to take a longer exposure for various reasons, for artsy effects. Or you might want to be looking at time dynamics. So you want another control over how much light gets in. And the way to do that is to put in an iris. We'll put in an iris which effectively cuts off a certain layer, a certain region of the lens, so that effectively, instead of getting a very big lens, you get a partial lens which still forms the same image, but it just lets in it lets in less light. The area has gone down, so you're just collecting fewer photons. The fancy word for this is called the aperture stop. Likewise, your film area, your developed area, or your CCD has to be big enough to collect all the light that comes in. And this is called the field. So your aperture stop determines how much light gets in. We'll call it D for diameter. And this is quantified by something called the F number. And it's defined as the focal length of your lens over the aperture stop. So by reducing your aperture stop, you have a smaller diameter, D, and therefore a larger F number. That means you'd actually have to expose longer. So large F means a longer exposure. And that is when you hear about lens speeds or camera speeds. So an F 2.8 is slower than an F2 because you'll have to expose for longer to get the same amount of light. It actually does something else. There's another aspect of this F number which is very important for photography, and that's called the depth of field. So let's think about how that works. Remember the basic picture here. If we have a lens, there's our camera, and we have a film here, and we want to take a picture of a scene. Let's say we have a picture of, I don't know, in front of a tree. Pardon my lack of art, but that's supposed to be someone standing in front of a tree. The tree is some distance z away. If we want to put the person into focus, the object is here, say, and that's going to look like this. There, we've brought in a point on the person into focus on the film. But how about the tree? Let's look at the tree now. Well, right, so the focal point is here for the tree, and here for the human will be focused there. So you get a sharp image of the focus. What you'll see, something that looks like this. You'll see a sharp, crisp image of a poorly drawn stick man. And in the background, you see a very fuzzy blur. This will be in focus, and this will be out of focus. Why is it out of focus? Because every point here is now wrapped to a big region in the background. I mean, we could always move the screen. Let's do that temporarily. Let's move the screen here. What are we going to see? We'll see a crisp image of a poorly drawn tree and an out of focus human. Our camera is only going to be able to resolve a certain pixel size anyways. If it's a CCD, it's the size of the pixels. Or less, or more, sorry, a bigger blur. Or if it's a film, it's going to be due to the chemical process of development. So we can tolerate a certain amount of blur. And the region under which the blur, due to the range of focuses, is under a certain region. It's called the depth of focus. Focus is the region which you have blur less than or equal to a certain amount. And we'll just call that in focus. So how does that help by lowering your F number? Well, let's put an aperture here now. Let's put an aperture stop in. We're going to block out this region. We'll block out this region. And we no longer get these rays coming in. So the blur we get on the screen has now been reduced. This is with the iris, which is the aperture stop, and this is no iris. We haven't blocked it down. We have a bigger blur. So by decreasing your aperture stop, the diameter, therefore increasing your F number, you get a slower lens, but you get a longer depth of field. And you can get images with very, very large depths of field. It looks very neat. But you have to expose them longer, typically. So that's the other thing, other way to control your image. If you're doing digital photography, there's one more. This doesn't work so well with analog photography, with film. It's called the ISO, just in case your photographer is out there. And that's effectively how sensitive your CCD is, how sensitive the pixels are. So ISO is one of them. The other two are controlling your aperture stop and your shutter speed. And you control how much light gets in and your depth of field. So you get images that look something like this, and we see we reduce by reducing the field stop here to there. We're reducing the blur due to the rays. We're letting less light in as well, and that's by changing your F number. So an iris, something like this, is what you're actually changing with this, and you get this F number scale. It goes up as square roots, because as you decrease the diameter, you decrease the area in terms of the square root, and the corresponding depth of field. You see that? So they move together. So as you increase your F number, you have a slower lens, but you increase your depth of field. And this is what a nice lens looks like on a camera. And what you're doing is you're moving the lens in and out and decreasing the field stop. So that's the basics by about how a camera works. So the last optical instrument we're going to talk about today is maybe the most important one, the eye. We'll look at the eye as an optical instrument. So the eye as an optical instrument has quite a few features which we might recognize, but it's also just near miraculous on how well we can see and how we can see it all. So, first of all, we have a lens and aqueous humor, which is a curved surface here. We have this curved surface, and we have n is approximately equal to 1.337 litres, and n is, say, air on the other side. And this curved surface here is a refractive imaging system. This is our refractive imaging system lens. We have a lens here which forms the image. We also have an aperture stop. The iris here, which adjusts to the light level, forms an aperture stop. We also have our version of the CCD, or the film. We have the receptors here. Here we have photoreceptors. There's about 10 to the 8 of them on the eye, and they're connected, as the output of our camera, to about 10 to the 6 optic nerves. So we have light coming in, forming an image on the back of the retina here, which is our photoreceptor. And there's about 10 to the 8 pixels, if you will, photoreceptors, and it goes to about 1/100th as much optical nerves. So there's compression. There's actually pre-processing that goes on the retina as multiple receptors are wired to multiple nerves as they send an image to the brain. The region where there's the most dense set of receptors is called the fovea. And there's two types of receptors, we should say. There's rods, which are highly sensitive to variations in light. Very light sensitive. And there's cones. And the cones have three levels, three different types, which are more sensitive to somewhere around the red, somewhere in the green, somewhere around the blue. And that gives us the sensation of color vision. And here's an example of the optical response of the rods nearly in the center there. And the different response, the wavelength dependent response of the blue, green, and red cones. You see there's a lot of overlap. Yet, so that when we're looking at 564 light, which looks fairly red, or we're even looking around here, we're getting both the green and the red firing, and that gives us a sensation of orange. And basically the relative weightings, along with a lot of pre-processing, is giving us this sensation of color. So look around you. Look around the room you see, and you see this vast array of different colors. That's due to the different weighting of these different rods and cones. There is the phenomenon of color blindness, and this is what a distribution, according to Wikipedia, sorry about this, is a distribution of cone cells in a colorblind person on the right versus someone without color blindness on the left. Now, I got to stop talking quickly because I'm fastly getting out of my pay grade. We're going to have to talk to a biologist to not make too many mistakes. But this is the basic physics of it. One other interesting fact, which you may or may not have seen, is the fact that this optic nerve comes in at a given point, we have a blind spot. So if I don't know, I'm going to draw this. I'm going to assume you have a roughly same scale computer as me. I'm going to do something like that. Maybe I should put it a bit further apart. I'm going to try this with you guys. So if you block one eye and you focus on the blue dot here and move your eye further and closer, up and down directly at it, I'm about 5 centimeters away. So my left eye is directly in front of this blue dot here. The cross will disappear. That's the location of this optic nerve here. And that really is a blind spot in your vision. Try it yourself, and you should be able to see that you actually have a blind spot at one point. So there's all these limitations we talked about. There's the depth of field, and there's a blind spot. There's an inversion of images. When we shone that lens onto the wall, we saw quite a mess. But look around you again, and you get this beautiful sensation of realistic imaging. And there's a lot of processing that goes on to give you that. So first of all, interestingly, there's a field called psychophysics in which they study things like the bandwidth of the human eye and how that pre-processing works. According to some studies, the bandwidth of the eye is about 10 megabits per second, which is less than YouTube right now. If you're watching this on YouTube and you're streaming on HD, that's actually more bandwidth than the eye. But look at this screen you're seeing here. It looks pretty good, but then look out your window. Look around you in the room. It seems like there's a much more vibrant sensation of vision. And that's because of this pre-processing. So here's a picture of what you might see, an image as physically cast to the retina. Okay, so here you see that? This is what the image on your retina would actually look like. Here we have a blind spot. Or a blind spot there. We have a low depth of focus. Low depth of focus or depth of field. We're only focusing on one spot. And we're inverted. We're inverted here. So this is what the image actually looks like on your retina. Well, if you're staring at this fella, this is what your image would actually look like in a retina when you're having a conversation with someone. But that's not what it looks like to you because of all the pre-processing that happens. So the eye is a pretty amazing thing. There's one more quite amazing thing that the eye does. Note that when we had a camera, we had to move the lens back and forth because different images will focus at different points. You cannot move the image back and forth. You can't move the lens back and forth or the retina back and forth in your eye because you're fixed at about a 1-inch diameter, which is roughly the diameter of the human eyeball. So how does the eye go about focusing on different things? That's called optical accommodation. In optical accommodation, you have muscles, the ciliary muscle, which contracts or relaxes and actually changes the focal length by changing the radius of curvature of the aqueous humor and lens combination so that you can focus on different objects. This is constantly moving, and muscles can't push, right? They can only pull. So it's a combination of your iris creating that opening and the ciliary muscles pulling with the different fibers that changes the radius of curvature. When you're maximally relaxed, you have the weakest lens. And that means you're looking at images at infinity. When your ciliary muscles are as flexed, as tight as they can give, that gives you the highest radius of curvature. So let's think about how that actually works. Optical accommodation. So let's take an image at infinity, meaning 10, 20 meters away. The rays are effectively parallel coming in. Your eye is fully relaxed. And that means a long focus. If you have good eyesight, that will form an image right on your retina. The furthest thing you can see without being blurry is called your far point. We'll talk about that in a sec. And let's bring an image closer now, an intermediate image. Your ciliary muscles are tightening now, and that creates a tighter focus so that you're still forming an image of that point directly to the retina. If you get even further, you're going to have maximally tightened muscles here, and your lens will still not be strong enough. so it will not focus. The closest thing you can see when your muscles are ciliary muscles are maximally constricted is going to be a given distance away. And that's called the near point. The near point is the closest point you can see without the image going out of focus. For kids, it's around 4 centimeters. For elderly, it can be up to 100 centimeters, a meter. And the average, the standard, is defined as 25 centimeters. I don't know, maybe it's just a survey. 25 centimeters. I went and asked a bunch of people. You can actually experience this. So do this experiment. Take a piece of paper or your screen and slowly focus on something. Get your eyes closer. You'll feel your eyes tensing, and then it'll go out of focus. That's your near point there. Mine is about just before 25 centimeters, it looks like. So try it out yourself. All right, so for the last part, let's talk about optical defects in your eyes and how to fix them. There's a couple different types. There's farsighted and nearsightedness, and there's also astigmatism. Astigmatism effectively means that the focal length is different along the, say, x-axis versus the y-axis. We'll talk about that a bit more in the coming lecture on aberrations. So for now, let's just look at farsightedness and nearsightedness. So nearsightedness, also known as myopia, is when your far point is not at infinity like it should be. So suppose that you're maximally relaxed. Your ciliary muscles are maximally relaxed, and you're looking at an image an object that's like infinitely far away. But still, the focal length is not long enough. The focal length is still too strong. Or rather, the lens is still too strong. That's called myopia. Far point is now no longer infinity, but some other point. So maximally relaxed, we're going to bring an object closer and closer. Eventually, still maximally relaxed, it's going to focus right in the back of the eye. So we'll say the far point is less than infinity. That is myopia. And how do we fix it? Well, if the lens is too strong, we're going to use the fact that dioptric strengths add, lenses add in the inverse, and we'll just weaken it up some. So we'll put a diverging lens in. So we have our object at infinity. We're now going to diverge the beam just a bit. And now we can bring our far point back out to infinity. So we use a diverging lens with a negative focal length to weaken the lens up when it's maximally relaxed. It can now image objects at infinity. And that's nearsightedness or myopia, when the lens is too strong. The other way is when your lens is too weak, farsightedness. In this case, your lens is too weak. You can easily see objects at infinity, but maybe you even have to be slightly, your eyes have to be slightly tensed when looking at distant objects. And it can lead to things like headaches and stuff. I'm not a real doctor, so don't quote me on any medical information. But farsightedness, you can typically see far, but your near point is much greater than 25 centimeters away. So this is called hyperopia. And when you have a maximally contracted ciliary muscles, that's the tightest focus you can get. The far point is still much greater than 25 centimeters away. Or rather, the near point is much greater than 25 centimeters away. So that if you put something at the near point, the supposed near point, it's just not going to, the lens is not going to be strong enough. So the fix is the opposite for the myopic vision. We put in an extra converging lens to increase the effective strength of your eyes. I've kind of drawn it in a goofy way here with these rays, but bear with me. Effectively, we've now brought our near point to the more reasonable 25 centimeters. And that's how eyeglasses work. It uses the fact that dioptric strengths add. So we can just add two lenses and get an effectively stronger or weaker lens. And we can tweak it up that way. It's a very simple idea. In fact, when you get your prescription, if you get glasses, as you may notice, I wear glasses myself. I have a prescription. I was trying to dig it up, but I think it's in my desk at UVic there, and while I'm recording this from home. So no luck, but let's just bring up what one might look like. Okay, so here's one. Doctors see more clearly. Haha, hilarious. That's bad even by my standards. But we have two columns here. We have the cylindrical part, which is the different focal lengths on different axes, and it gives you the angle of that axis. Let's postpone that until we talk about aberrations. But here we see the spherical is negative 1.25 and negative 2.25 between the eyes. This is literally the dioptric strength. So the focal length of this lens, person's lens, is 1 over 1.25 meters and negative 1 over 2.25. So is this person nearsighted or farsighted? We can see that they have negative, let's just see, from here we have F inverse was negative 1.25. So the focal length was negative 80 centimeters. And that would be their right eye. The left eye was 2.25, which is 9/4, so 4/9 for the other eye, which is 0.444. So a stronger diverging lens in the other eye, but effectively it's just diopters, the dioptric strength, and that's literally tuned by the radius of curvature of the lens. So you have a very sharp, steep curvature for a strong lens, and a weak one curvature, almost flat for a very weak lens. There's in fact an instrument called a Diopter Gage, by the way, which does this. This is what the gauge looks like, and it's literally just looking at the radius of curvature, and it gives you whether or not you have a positive, or if you're pressing this in, it's negative. It would be something like that. Lens, knowing the index of refraction of the glass, it just uses that lens maker's equation that we used before to actually tell you the image strength. And that's how you'd actually physically measure the strength of eyeglasses without casting an image. And that's basically it for lecture 28. Lecture 29 we'll talk about magnifying glasses, telescopes, or microscopes. And finally, after that, we'll talk about aberrations, and that'll about do us for the course. So we're getting close to the end, but a few more exciting things to do first.